Welcome. So in our last class we have studied and did a thorough analysis of inverting and non-inverting amplifiers using op-amp. So next thing we should do is of course an analysis on difference amplifier. But before that let's ask a question. What happens if we by chance or by mistake swap or change the plus minus terminal of the op amp in either of these circuits? So say consider this circuit. This is a inverting amplifier. Let me copy it. Okay, so this is the correct circuit of an inverting amplifier. Now, what happens if we by chance or by mistake make this as plus and this one as minus? Okay, so the question is, what happens if we swap the inverting and non-inverting terminals, plus and minus inputs in an this is inverting amplifier. Originally it was inverting amplifier. In an inverting amplifier. So this is the swapped the circuit with swapped terminals. So this is the wrong circuit. Okay, we should have minus here and plus here, but I have the wrong circuit. I have plus here and minus here. So what will happen? How do we analyze it? Okay, so let's study that. So once again, what we have to do is find the answer to the question, what will be the value of output VO if we know the value of input V1. So given V1, VO will be how much? So this is what we have to find out for this wrong circuit. But the process that we will follow is once again same. We will find out the first we have to find the unknowns that we have to solve for. So the unknowns are of course VO output and here Vn. Okay, V1 is given and Vp is equal to 0. So these are knowns. V1 is given and Vp is equal to 0. So we have two unknowns. So now to find or solve for these two unknowns, we need two relationships. Now these two relationships, one of course will come from here, okay, from this part of the circuit, which is the series combination of R1 and R2. So we can find the current here and then apply potential divider rule, which we did before. So let me write it quickly. So Vn will be equal to VO. So it will be some sort of average of VO and V1. Average of VO and V1 because Vn is in between VO and V1. Okay. So the rule, you can remember this, it will be VO multiplied by R1 divided by R1 plus R2 plus V1 multiplied by R2 divided by R1 plus R2. So it's a weighted average of VO and V1, and the weight is the weight associated to VO is proportional to R1. So VO is farther from R1 and closer to R2. Therefore, we have VO multiplied by R1, the resistance which is further, and with V1 we have R2, that means the resistance which is farther from V1. So this is the rule for Vn. So this is one relation. You can also derive it by finding the current and then adding the voltage drop here, the way we did it in the last class. Okay, here we did that. Okay, so and you see we have the same pretty much the same result. Okay, so this is a quicker way of doing it. Okay, now from this we can write VO in terms of Vn. So this will become Vn multiplied by R1 plus R2. Okay, so Vn multiplied by this factor minus V1 R2 and whole divided by this R1. So this is relationship number 1. And the second relationship will of course come from the static characteristic of the op amp. So I will do this now a bit quickly because we have done this already twice, and we are now a bit more matured, so we can do it little quicker. Okay, so the second relationship is the static characteristic, which is here we have Vp minus Vn, here we have VO, and the characteristic looks like this. For an ideal op amp, this line goes very close to the y-axis and like this. So this is the static characteristic. Okay, now okay, there is a mistake. The mistake is that a small mistake. So Vn is now the voltage at the plus terminal. Okay, and Vp is now the voltage at minus terminal. Okay, so because I have changed this sign. So let me just change these names. Let me make Vn equal to Vp and Vp equal to Vn, so that N stands for negative and P stands for positive. So everywhere now I have to make this N and this P. This is P, this is P. Anywhere else? Yeah, here. This is P. Okay. So because this is now Vp, this is now Vn. Okay. Vn0, Vp is this much. Yeah, I guess everything is correct. Okay. So now Vn is equal to 0 here. So therefore this I can write simply as equal to Vp, since Vn is equal to 0. Therefore this is the curve relation between Vp and VO. So this is one relation which comes from the static characteristic of the op amp, and the other relationship is this, which comes from the external circuit potential divider, kind of potential divider rule here. So now let's plot them together. So this is the static characteristic, and let me draw this curve. Okay, so this curve is VO or y-axis. Y is equal to, this is called this x-axis, x multiplied by m minus some constant, because V1 is given. So this is y equal to mx minus c. Okay, so that curve will look like this, mx minus c. So the slope will be positive but the intercept will be negative, like this. Okay, so the intercept is negative because this is negative, assuming V1 positive, and this is the slope here is of course positive because resistances are positive. So now what will be the solution? You see, these two curves intersects at 3 points, 1, 2, 3. That means there are possibly 3 solutions. So this is one this is one solution, this is another solution, and this is another solution. So we have 3 possible solutions. Okay, you can call them as give them some names. This point as A, this point as B, this point as C. Okay, so we have 3 possible solutions for the unknown Vp and Vo. If the solution is this, then output Vo will be minus V supply. Okay, so let me write them: A, B and C. For A, we have output Vo equal to minus V supply. This is minus V supply, and Vp is equal to something. Vp is this much. Okay, something. I'm not writing this. Something. And here for point B, we have Vo equal to something between minus V supply and plus V supply. So here let's write this is minus V supply less than Vo less than V supply, and Vp, this is 0, almost 0. Vp is equal to or almost equal to 0. And for point C, we will have Vo output equal to V supply plus V supply, and Vp is again something. So this will this if you drop a vertical line, this will be the value of Vp. Once again, here in this case for A, if you drop a vertical line here, this will be the value of Vp. Something. Let me write this something. Okay, so there are 3 possible solutions because we have 3 intercepts sections. Okay, so but output cannot take 3 values at the same time. Output can take only one value. So which value will it take? Will it take A, or will it take B, or will it take C? So that's right, but output cannot take 3 values at the same time. So which value will it take? Let me tell you the answer. The answer is that we will show you or justify you that the point B, which is this point, is an unstable solution. The point B is an unstable solution. Therefore, it is unlikely that the solution will be or V output will be at this value. Okay, so therefore, it is unlikely, almost impossible, that VO will stay at B. So the output cannot take the value which is suggested by the solution B. So it will then take, so therefore VO will stay at, or I may say the solution will stay at A or B, not B, C. A or C, that means VO will be equal to minus V supply or plus V supply, minus V supply or plus V supply. Still we have two possibilities. Which one? So which one will the output take? And the answer is it will depend on the past history of VO or the previous value of VO. Okay, depending on the previous value of VO. So this is what I am going to justify. So first let me justify why point B is not stable. So for that, let me just copy this. So let me first tell that why point B is not stable or unstable. For that, assume that at some moment the output is, the solution is here, is at point B. Okay, at some moment, say this is here. But then due to some disturbance, due to whatever the reason is, say the output VO changes a bit. Okay, it can go up a bit slightly or go down slightly due to whatever reason you can think of. And this op amp is an IC, so the output may depend also on this voltage supplies, and say also if the voltage supply have some noise, that will also affect VO, or whatever the reason is. VO can fluctuate a bit, it can go up a bit or go down a bit. Now what will happen if VO goes up a bit? Okay, if this point, this value is increased a bit, then the value at Vp will also increase, assuming V1 is constant, it's not changing. Say if this increases slightly, then of course Vp is some sort of average of V1 and VO. So if VO increases, Vp will increase. Also here you can see if this increases, this is constant, then Vp will increase. Okay, so Vp must lie on this line. Vp must lie on this line. Okay, so the VO versus Vp point, that must lie on this line, because this R1 and R2 and V1, none of them are changing, because this line is defined by R1, R2, R1, V1, all these values are not changing, therefore this line will remain same. Now if VO increases a bit, Vp will also increase a bit. So this, if I start from here, I will move slightly here, okay, like this. Okay, but as I must lie on this line. Okay, so I can go a bit like this. So now if I go a bit like this, if I come here, say, then at this value of Vp, so at this point, okay, let me show the same thing in this diagram without making that clumsy. Okay, so if I move from here to here at this point slightly, this is a slight movement, small change, although I'm drawing a significant amount, but assume this is a small change. Now what happens? The static characteristic or the property of the op amp that says that at this value of input, okay, so now this is the value of Vp or Vp minus Vn, because Vn is 0. So now at this point, by dropping a perpendicular from this new point, so at this point the output of the op amp should be this much. Okay, so therefore the op amp will now try to increase its output and match this characteristic, because op amp believes on this property, this static characteristic. So the op amp, when sees the input Vp minus Vn is here, it will try to increase its output to this value. Therefore Vo will increase further. So what will happen? This point will move towards the right further. Okay, and say now if it comes here, let me zoom in. Okay, so now if it comes here, okay, then it will see the output should be this much, Vo should be here. Okay, so the op amp will try to increase its output further. So this way what will happen, this point will move gradually like this and will come here at this point, point C. Then the op amp will see, okay, now I am simultaneously on this green line, because I am not allowed to move away from a green line, but I am also on this black line, this static characteristic. So then the op amp will be happy, because for this value of input, this is exactly what the output should be from the static characteristic. So this is where the op amp will stop. This is where the op amp will become happy. So if I start from this point and by any chance move a bit towards the right by a slight increment of the output Vo due to whatever reason, that will cause further increment of output, and this will go on in a chain until and unless I reach this point. Similarly, if I have a small change in the opposite direction, say output is reduced by a small amount, then from this point I come here. I am not allowed to leave this green line. Okay, I must always stay on this green line, because that is the relationship which I obtain from the potential divider rule here. So if output decreases, I'll come here, and now at this value of input, so now this is the input to the op amp, so this is the input to the op amp. Now for this input, the output of op amp should be here, which is less than the current Vo. So what will happen? The output will decrease further. So I will move down further here, and then once again for this input, this should be the output of the op amp. So op amp will try to decrease its output further. So I will keep moving like this until I come at this point, point A, where the op amp will be happy again, because now this point lies on the static characteristic of the op amp. So the op amp will be happy. So if I move slightly towards the right or slightly towards the left, I will go and hit this point C, or in the opposite direction and hit this point A. So this point is unstable. Okay, so this is why this point B is unstable. Now let's see, are these points A and C stable? Okay, so let's check, are these points, so point B is unstable, But okay, now let's ask, is C stable? Okay, so let's focus on this part. Now say I start from this point, and by some chance I move a bit away from this. Say the output is increased, VO is increased, therefore I come here. Okay, again a small change. So I come from here to here, and then at this point, so this is the value of Vp minus Vn, and the static characteristic of op amp will say that for this value of Vp minus Vn, the output of op amp should be here. So the op amp will now try to decrease the value of VO. Why? Because it has higher value of output than it should have according to the static characteristic. So now VO will decrease. VO will decrease means what? Now I will come back in the opposite direction. Okay, and I will come back to point C. Similarly, if I move a bit in this direction, say I come starting from here, I come to this point, due to a small change in VO, I cannot leave this green line. So now this is the value of Vp minus Vn. So at this value of Vp minus Vn, this should be the output of the op amp, but the actual output is here. So the op amp will think, no, I have to increase my output. So it will increase the output, and therefore I will go back once again towards the point C. So if I move away from here to here, I will go back. If I move away from here to here, I will go back. Therefore this is a point which is stable, because if I move away, I go back. Okay, so is point C stable? Yes. Similarly, you can show that A, this point, is also stable. Okay, now so I have tried to justify why this point B is not stable, and these two are the only stable solutions, A and C. A and C. Okay, now the next question is, so what will be the output? Will the solution be A or will it be C? Okay, I am telling you it depends on the previous value of the output, the history of the output. So okay, let me so let us now focus on this circuit. Okay, so say at some moment the value of VO is plus V supply. Okay, so let's make a guess, not guess, say at some moment this is equal to plus V supply. At some moment. Now if say, let me just take a concrete example. Let me call this V supply equal to 15 volt. So this will be minus 15 volt. Okay, let me choose the value of input V1 equal to say 5 volt. Example. Now this is equal to 15. At some moment, Okay, so this is 15 volt, this is 5 volt, and let's take all these resistances equal to 1 kilo ohm. 1 kilo ohm, R2 equals 1 kilo ohm for ease of calculation. Therefore, Vp will be what? Vp will be just an average of V1 and Vo. Okay, so in this expression, or here, if I put 1, 1, 1, so this is half. So 1, 1, 1, this is also half. So Vp will be average of Vo and V1. Vo by 2, V1 by 2. So then Vp will be equal to 10 volt. This is 5, this is 15, this will be average 10 volt. Now if this is 10 volt, Vp is 10 volt, Vn is 0 volt. Okay, so this op amp sees that Vn is 0 volt, Vp is 10 volt, this is higher. Therefore output will be, of course, equal to positive V supply, 15 volt. So it will stay at that value happily, it will not change its output. Okay, so if I start from the value of 15 volt at the output, then that means this is equal to 10 volt and this is higher than Vn. So therefore output will remain at its value 15 volt, because op amp behaves like a comparator. What it does, it compares Vp and Vn, and if Vp is higher, it increases output. If Vp is lower, it decreases output. That's what it does. Now let's take another example, another case where, say, we have this equal to minus 15 volt. So this point is at minus 15 volt, but the input I am taking the same value, 5 volt. So what will be this value? Average of this and this. So then 5 and minus 15. So this will be, average will be plus 5. So this will be 5 volt, because 5 minus 15 is it will be minus 5. 5 minus 15 is minus 10, divided by 2 is minus 5. Okay, so this will be minus 5. Now that means this is 0, this is minus 5. So Vp is lower, and if Vp is lower, what will the op amp do? Op amp will keep its output at the minus V supply, that is minus 15 volt. So it will stay happily there, it is not going to change its output. So therefore we see that in this example, the output will depend on the previous value of the VO. If we start from the assumption that VO is minus 15 volt, then it will stay at minus 15 volt. If we assume that it starts from plus 15 volt, it will stay at plus 15 volt. It's not going to change. So in this example, so we observe that, let me write. So we observe that if we start with VO equal to plus 15 volt, the op amp stays happily at the same value. But if we start from VO equal to minus 15 volt, then op amp stays at VO equal to minus 15 volt. So it depends on the previous value. Okay, so let me let's summarize what we have seen. So a small summary. So we have started with the question that, what happens if we swap or alter by mistake the plus minus inputs of an this is inverting amplifier. Okay, original inverting amplifier should have minus terminal here and plus terminal here. So by mistake if we swap it, what happens? The question is, will it still behave like an amplifier? Will it be the case that VO is equal to V1 multiplied by some constant like we had previously? For the original inverting amplifier, it was minus R2 by R1 times V1. Will it be so? And in this detailed analysis we see, no, the output will not be equal to V1 multiplied by R1 R2, sorry, R multiplied by R2 by R1. It will not be so. Instead, output will be either positive supply for V supply or minus V supply. Okay, so this we call the output will go to saturation, positive saturation or negative saturation. And which one will it go to? That depends on the previous value of VO. So if by chance, let me say it in other way, if by any chance output goes to plus V supply, it will stay there happily, no problem. That is a valid stable solution. If output goes to this point by any chance, it will stay there again happily forever. But the output is not going to be input V1 multiplied by R minus R2 by R1. No, it's not an amplifier. It's not going to work like an amplifier. That is because this point is unstable. It will not stay here. Okay. So the answer, let me write, it will not behave like amplifier, it will go to saturation plus or minus. We have seen it with thorough analysis. And also another observation, very nice observation, will virtual sorting, the concept of virtual sorting be valid in this wrong circuit? Will Vp equal to Vn? No. Why? Vn is 0, but how much is Vp? So suppose if I land up here at this point C, then Vp is this much. Okay, then Vp is this much, which is here to here, which is not 0, it is positive, but Vn is 0. Okay, so here at this point Vp greater than 0, Vn equal to 0. Similarly, if I land up at this point, I will have Vp less than 0, this much. Okay, this will be the value of Vp, but Vn equal to 0. So Vp is not equal to Vn unless at this point. Yes, at this point Vp will be Vn because both are so Vp is also 0, but this is not a stable point. This is not a point that we are likely to have. So virtual sorting is not true for this circuit. Okay, so that's why I said virtual sorting is not a property of op amp in general. It is a property of this circuit, some special circuits, not of all circuits. this circuit doesn't work with the concept of virtual sorting. Okay, so one small note, you cannot, if I give you this circuit and ask you the question that V1 is 5 volt, what will be VO? You cannot do the analysis with the assumption Vp equal to Vn, so Vp is equal to 0. No, that method will not work. Okay, so that is because virtual sorting is not true for this circuit. We will come back to this circuit again later. This is a very useful circuit. Although this is a wrong circuit, but this is also a very useful circuit. This has a name. This is called Schmitt Trigger. SCHMITT, I guess the spelling is trigger. We will come back to this circuit again and again. Thank you.